Hi, good morning, students. Welcome to today's class. In this class, we'll be seeing on functional forms of regression models. We are very clear about what regression is, right? And here we'll be seeing various forms of regression. By regression, we actually mean linear regression, right? That is, what is the average effect of X variable over Y by keeping other X variables constant. If you have got X variables, we mean independent variables or explanatory variables. By making constant set risk variables, other independent variables, what is the average effect of one independent variable over the dependent variable? So it's a functional relationship between Y and X. So this is what regression is. So here the functional forms of regression, the most basic functional forms that we use in economics. For example, what we have is we have log linear model, we have log-LIN model, we have LIN-LOG model, reciprocal model, and polynomial model. So all these are basic functional forms which we use. As you could see here, it is log linear. This is also called as double log model. So double log, it means what? We are taking log on both sides. By log, I mean natural log. So we are taking natural log on both sides. It means we are taking the natural log of Y as well as natural log of X. That is what is called as double log model, or it is log linear model. So this log linear should not be confused with log-LIN model. So log-LIN is different, log linear is different. By log linear, I'm saying you that we are taking log on both Y as well as X. So it is double log model. And then what we have log-LIN model. So we are taking log on Y and not on X. So Y log and X as such. So this is log-LIN model. So always you see in this way, first we are taking log of Y and then we are proceeding to take log on X. So that is the step. First Y and then X. So Y is dependent variable and X is independent variable. So we'll focus on what we have in dependent, right? And then what we have is LIN-LOG model. What is LIN? LIN is, so we are using the data as such of the Y variable, but we are taking log of X variable. So LIN-LOG. So keeping Y as such and then taking log of the values of the independent variable, that is X, it is LIN-LOG, and then reciprocal model, and then what we have is polynomial model. Now you could see log linear model is what? In which both the dependent variable, that is Y, and the explanatory variable X are in logarithmic form. So both are in log form. And in log-LIN model, so first we are taking the log of Y and then X, right? So you see now, this is also called as growth model, in which only the dependent variable is logarithmic, but the independent variable is linear. Okay, so we are taking log of only the dependent variable and the independent variable is linear. So this is also called as growth model. We can use this model, in if you want to measure the growth of anything like compound growth rate of GDP, compound growth rate of area, production, productivity, we can use this model, log-LIN. And then LIN-LOG model, in which the dependent variable is linear, but the independent variable is in log form. So we are taking the log of the values of the independent variable because it is LIN-LOG, and we are keeping the values of dependent variable as such. Then reciprocal model, in which you see the dependent variable is linear, but the independent variable is not. Okay, so linearity is only in the case of dependent variable, but the independent variable is not. We know about the OLS assumptions. We need to ensure linearity only in parameters. Whether the variable is linear or not linear, it is not of any significance to us. We mean a model is linear if the parameters in it are linear. Okay, if the beta 2, that is a slope, right? If the slope parameter is linear, it means the model is linear. Whether the variable, it can be dependent, it can be independent, whether the variable is linear or not, it is immaterial to us. Then what we have is we have polynomial model, in which the independent variable has got various powers. For example, it can be a quadratic model, it can be a cubic model, So independent variable will come with powers like x squared, x cubed. So that is what is polynomial model. So all these are the basic models, which we can say as functional forms of regression models. Now, how to interpret it? We know about the interpretation linear model. If it is simply y equal to a plus bx, it's a linear model, right? So what we'll interpret, if x is changing by 1 unit, what is the change in y, keeping other variables constant? Because if you have got if you have got 2 or 3 independent variables, then we'll interpret in this way. If x changes by 1 unit, what is the change in x? So that is what is given by your linear model simply. But now if we have log linear, log lin, lin log, then how to interpret? So this is very important. We'll see now one by one. Okay, now before going into details, let us have some clarification. Even though we know it, what is log, what is natural log, let us have some more clarification in it. Okay, like we are going to refresh it. Okay, what is log and natural log? Both are different. For log, if I say log of any value, then what we're actually doing is we are taking, we are keeping the base as 10. Just a minute. I have to attend a call now. Just a minute. That's one. Yeah. Yeah. Oh, बोलो हाँ आप गए थे ना अटेंड नहीं किया था ना then you have to contact register office. This is not the place to contact ना. If you want a refund, only register office can answer ना. They cannot answer you, right? Yeah, right there. Now, as I was telling you, the difference between log and natural log. So log is what? The base is 10. So if the acreage of cotton in Junagadh is 28,250 hectares, and if you want to make a log of it, then what you're actually doing is, you are saying 10 raised to the power of what gives you 28250. If this is big number, 28,250, then 10 raised to the power what gives you 28,250. So the log of 28,250 is 4.45 because the log base is 10. So 10 raised to the power 4.4510184552 gives you 28,250. So this is natural log base 10. But if the base is not 10, if the base is E, this is called natural log. Here the log base is 10. In case of natural log, the log base is E. Okay. So what is the value of E? It is 2.718. So if I'm taking natural log of 28,250, it means what? E raised to the power of what gives you 28,250. E raised to the power of what? So if E value is 2.718, so 2.718 to the power 10.24885 will give us the number 28,250. So this is what is log and natural log. In log base is 10. So if base is 10, then 10 raised to the power of what gives you your number. Your number is 28,250. For example, in Junagadh, if the acreage of cotton is 18 lakh hectares. So if 18 lakh hectare, you won't be able to plot it graphically because you're dealing with so many crops and you want to bring the acreage of all the crops in one graph. Then sometimes it is difficult in the case if for one crop the area is huge and for the other crop the area is small, you won't be able to plot in a graph. So you have to take log of it for the sake of convenience. So if the area of cotton in Junagadh is like at 2250, you can take log of it. Simply log base 10 is 10 raised to the power of what gives you this number. So 10 raised to the power of 4.45 10 can give us 2250. So simply in Excel, you can go for log of this is giving you this. So 10 raised to the power of 4.45 gives you a number. In case of natural log, what you do is instead of LOG, typing LOG in Excel, you can simply go for typing LN, log, natural log. So LN 28250 gives you 10.24885. Are you getting it? So then you can also take anti-log of it. If you want to take anti-log, then Excel, in the case of natural log, what you can do is you can go for EXP, exponential. So EXP of this. So in Excel, you type is equal to EXP 10.24885 will give you this one. In the case of log, there you have to mention the base. The base has to be mentioned. So then how you'll be taking anti-log of this? So then where in the case of natural log, you're going for EXP. right? In Excel, if you want to take antilog of this, what you do is, then in Excel, you have to type the formula is equal to power, P-O-W-E-R, power, then mention the base. Base is what? Base is 10. And then what your value is, 4.45. So power within brackets 10, 4.45101845 will give you this one. So that is the antilog. So we have variations in taking antilog of natural log as well as log base 10. Okay. So this is what log and natural log is. Now I think we are clear about what log is. So if simply I'm taking log, it means log base 10, 10 raised to the power of what gives you a number, right? The number in which you want to find the log of it. Then if you are taking natural log, not just log, in natural log we have E, so log base E. So E raised to the power of what gives you an actual number. So this is what log and natural log is, which is very important. In the case of here, in the regressional functional forms, in functional forms of regression, what we are doing is we are taking only natural log. We are not bothered about the log base 10. Okay. So now here, so this is log-log model, log linear, double log or log-log model. So what we are doing over here, you can see this is your dependent variable. Yi is equal to beta 1 x to the power beta 2 e to the power ui. So here we have the error term as well. So econometric model, you can differentiate from that of a mathematical model with the help of this one, error term. If the error term is not present, you can say it's a mathematical model. So with the help of an error term, we are establishing econometric model, right? So you can express this alternatively as you see, taking natural log on both sides. So log yi is equal to log beta 1 plus beta 2 log xi plus ui. Okay. So here natural log, as I told you, the value of e is 2.718. Okay. Now you can see this model is linear in parameters, right? The model is linear in parameters because in parameter, you can see beta 2 or beta 1, whatever it is raised to the power 1. So it is linear in parameters. If, for example, we have beta 2 squared, it means beta 2 is raised to the power 2. It means what? The model is linear in variables, but it is not linear in parameters. Then that's a problem to you. You won't be able to interpret properly. Okay. So the model is linear in parameters. Then whatever assumptions we have seen in the case of classical linear regression, all these assumptions hold for this model. And what we have is, we'll be estimating alpha hat and beta 2 hat. So alpha hat, it's for the intercept, and beta 2 hat for slope. Okay, so alpha hat and beta 2 hat, which you'll be estimating, will be the best linear unbiased estimators blue of alpha and beta 2. So alpha and beta 2 are they pertain to the population, right? And alpha hat and beta 2 hat, they pertain to sample, right? So this log-log model is best to calculate elasticities because whatever the coefficient of the slope, coefficient that you're getting in the case of the slope, that itself is sufficient for you to elastic because the value of slope itself is the elasticity of the model. So this is very much important. For example, here you are getting a value, right? For example, it is 0.4. So 0.4 is the value of the slope. That itself is the value of the elasticity. Okay. So that is why it is also called as constant elasticities model. Okay. In the case of other models, be it log-LIN, LIN-LOG model, there the value of the slope itself won't be elasticity, right? So you have to work with elasticity using formula. We'll be seeing one by one what are the formulas that we have to use to calculate elasticities. Okay, so this is log-log model. You see why it is called? Because the slope coefficient measures elasticity of y with result. So the slope coefficient beta 2 itself, it measures the elasticity of y with respect to x. So what is beta 2 here? It shows the percentage change in y for a given percentage change in x. This is what your elasticity is, right? Percentage change in x to the percentage change in y. Now, so this is your dependent variable, right? Production of wheat. Okay, and then we have purchase price of wheat. Okay. So this be dependent variable and this be independent variable, y and x, and we are taking log of both. This is double log model, and what we are getting is we'll be getting a regressional function form of like this. Okay, so y equal to 1693.7 x to the power 0.0476. Okay, so how to interpret this? In the case of linear, if it is y equal to a plus bx, we know how to interpret, right? But here we have to interpret in terms of percentage. You see, increase in price of wheat by 1% leads to 0.0476 percentage change in production of wheat. So wheat. Okay, so if the model is double log, then we have to interpret in terms of percentage. Okay, so increase in independent variable by 1% leads to increase or decrease in dependent variable by so and so percent. So this is what your interpretation is. Okay. Now coming to log-LIN model. So as the name indicates, log-LIN, it means what? First y and then x, right? So we are taking log of y and then we are keeping x as such. So this is the PR of population regression function. In the case of log-LIN model is yi is equal to beta 1 e to the power beta 2 xi e to the power ui. And then we are taking, this is the population regression coefficient, beta 1, beta 2, and ui is the residual term. And for the sample data, we are using hat or cap. Okay, and then so if you're taking log on both sides, what we have is we have log y is equal to log beta 1 plus beta 2 xi plus u. You see, in xi we don't have log. In the case of double log model, log we had ln, that is log on y as well as log on x. Here we have log only on y and not on x. So this is why it is called as log-LIN model. So how to interpret here? The interpretation is, if x increases by 1 unit, then y increases by the slope into 100%. Okay, good. Log-LIN model. If x increases by 1 unit, okay, then y increases by beta 2 times 100%. So this log-LIN model is also called as growth model. It is very much useful in growth. For example, if x be your time period, for example, from 1986 to 2020. So we have time period. And then in y we have GDP. If you have to find what is the growth rate in GDP, then if the x is increasing by one time period, then over the time period, what we have is, we have the growth rate in GDP, which increased by beta 2, that is slope, into 100%. So this is very much useful in terms of estimating the growth rate of anything, be it population, be it GDP, be it agriculture income, be it area, production, productivity. But here in growth rate, we have to keep in mind, we have instantaneous growth rate as well as compound growth rate. Compound growth rate is over the time period. Instantaneous is for the time period. For one time period, we have instantaneous. Then if you have to work out growth rate over the time period, that is from 1986 to 2020, the growth rate over the time period can be estimated by the same log-LIN model, but with a slight modification. We'll see what the modification is. Okay. Now to measure growth rate, we can apply log-LIN model. Economists, business people, governments can use. Okay, so we have the dependent variable, which is y. It can be anything. It can be GDP, it can be agri income, it can be area, production, productivity, and your x, that is independent variable, is time period. Okay, so we have to see growth rate over time, compound. We know the principle of compounding, right? You might have read in your 6th semester agriculture economics course, farm management and production economics, where the principle of compounding. What is compounding? Compounding is what? The future value of present money. You have to find the future value of present money for which you'll be using compounding. And what is discounting? The present value of future money. At present, you don't have any money, but in future, you'll be getting some money. So what is the present value of future money? That is discounting. For example, if a farmer is going to invest in coconut orchard, he'll be getting his investment back only after 5 years. So what is the present value of the money that the farmer is going to get after 5 years? That is what discounting is. Okay. So here the formula is very simple, right? The formula of compounding. This is the present value plus 1 plus r to the power t. So yt is future value, right? What is the future value of present money? That is what compounding is, right? So similarly, you're going to use for growth rate, same thing. So here we will be taking log on both sides. So then what will happen? Log of yt. So log of y, and you see t is your independent variable. So log yt, log y0 initial time period, plus t log 1 plus r. So this is your slope coefficient, right? And then here t is your independent variable, right? then what will happen is, then the beta 2, right? This beta 2, which is a slope, it gives log 1 plus r. So log 1 plus r is your beta 2. So if you're taking partial derivative of it, so d log y upon dx will give you 1 by y dy by y by dt here, which is equal to delta y by y upon delta t. So this delta y by y is nothing but beta 2 delta t. Okay, and then what you'll get is 100 into beta 2. That is, you're multiplying the slope with 100 will give you the change in terms of percentage over the time period. So 100 times beta 2 gives the growth rate in y. So whatever beta 2 you are getting, for example, how you'll be estimating this, beta 2? By simply, for example, in y, what you'll have is, you'll be having GDP. Okay, GDP over the time period. So the time period is, for example, 1986 to 2020. So let us give 1 to 34. So in T, you'll be having 1, 2, 3, 4, 5, 6 to 34. And then Y, you'll be having GDP to the corresponding year. Okay, instead of year, you are mentioning 1, 2, 3 in a series because you have to introduce in the model. And then you have GDP. It can be from 20,000 20,000 crore to, right now the GDP is what is that, 180 billion, 180 billion, that is present GDP. So from 20,000 crore to 20,000 lakh, whatever the number is, to 180 billion, the present money. So you can have that. Okay, then what you're doing is, you're transforming only the y variable. That is, you're taking log of y. So keeping x as such, taking log of y, then you can use your Excel. There in data analysis, you have a regression package. You can introduce y variable as well as x variable. Okay, and then when you regress, then what you'll be getting is, you'll be getting the slope coefficient in a beta 2, right? And this beta 2, which you'll be getting, okay, and you have to multiply with 100, will give you growth rate simply. But the thing is, we are not interested in instantaneous growth rate, but we are interested in compound growth rate over the time period. Okay, then how to find that? Okay, so here what we are getting, as you could see here, this is time period, your x, and this is your y. You have to take log of it. Okay, and then when you do regression, what you'll be getting is 0.06. This is comma, you should interpret it as point, okay, period. So 0.0621. So this 0.0621 is your beta 2. So 0.0621 into 100, it means what? 6.21. So 6.21% is your growth rate, into 100. So that is a growth rate. So if x changes by 1 unit, y changes by 0.0621 into 100, that is 6.21%. Okay, so this is what is your log-LIN model. Okay, now the thing is that the coefficient of a trend variable, okay, whatever the coefficient you have, slope coefficient, it gives you instantaneous rate of growth, that is at a point of time. But what we are interested in is, we have to find the compound growth rate, that is growth rate over the period of time. So for that, what we are going to do is, we can easily find out by taking first anti-log of the slope coefficient. If beta 2 is 0.0621, you take anti-log of it. So as I told you in the previous slide, we can take anti-log of a ln, natural log, then by exp in Excel, then 0.0621. Okay, this will give you anti-log, right? Then minus 1, okay, is equal to, why are you doing minus 1? Because that's the formula to find out the compound growth rate. So anti-log of beta 2 minus 1, okay, into 100. So exp 0.0621 minus 1 will give you 0.0641 into 100, that is 6.41. So that 6.41% is the CGR, compound growth rate. So 6.21, which you obtained in the previous slide, is the instantaneous at a point of time. But over the time period, if you want to find the compound growth rate, you can very well use it by just finding the anti-log of the slope. If the slope is 0.0621, what you can do is you take anti-log of it. It's very simple in Excel. Simply use the formula EXP. So EXP is 0.0621, which will give you the anti-log of it. Then -1, and you'll be getting 0.0641 into 100. That is 6.41% per year. So this is the compound growth rate. Okay. Now, LIN-LOG model. LIN-LOG model, you see, the Y values, we are keeping it as such. We are taking log of only the X values, the independent variable value. So the PRF is nothing but YI is equal to beta1 plus beta2 log XI plus UI. You see, you're making log of the independent variable, not of the dependent variable. Okay. Then the slope coefficient we can easily obtain by this beta2 is your slope, right? So delta Y divided by delta X by X. So this will give you the slope coefficient. Now, how to interpret? So here, if X changes by 1%, if X is changing by 1%, then Y changes by beta2 divided by 100. If X changes by 1%, then Y changes by beta, whatever value you're getting, beta2 divided by 100. Or if you're dividing 1 by 100, you'll be getting 0.01. Okay, so you can multiply 0.01 into beta2 value. Okay, so in Excel, what you'll do is, if you are given Y and X and you are asked to find the LIN-LOG model, then you have to use Y as such. You have to take only log of the X variable, the values of X, you have to take of it, and then you have to run regression, and then you'll be getting the beta2 slope coefficient value. And we are having the slope coefficient, and then I'm asking you to interpret it. Then what you can interpret is, if X is changing by 1%, then Y will change by 0.01 times beta2, or beta2 hat by 100. So that is the interpretation in LIN-LOG model. In the case of log-LIN, it was different. In the case of LIN-LOG, it is different. So just a minute. Okay, welcome back. So here, the interpretation is different in the case of LIN-LOG. If you are changing X by 1%, if X is changed by 1%, then the Y changes by 0.01 times the slope coefficient, or the slope coefficient divided by 100. So this is what your LIN-LOG model is. Now you can see this one. So here we have the time period, we have GDP, and we have M2. So the GDP is your Y variable, M2 is your independent variable. Okay, what you're doing is, this is LIN-LOG model, right? Yeah, LIN-LOG model. So you're keeping GDP as such, and you're taking log of M2. And then when you're running the model, what you're getting is 10359 log X minus. So this is the intercept, doesn't matter. And this is your R squared value, 0.86. It means what? 86% of the model is explained with the independent variable that you have taken. So now, if the beta2 hat, that is a slope coefficient value, is 10359. So if X increases by 1%, then Y increases by 103.59 unit, because beta2 by 100, right? So if X is increasing, your M2 is increasing 1%, the Y is increasing by, Y or GDP increases by 103.59, whatever the unit is. Okay, so this is what is your LIN-LOG model. Okay, then coming to reciprocal function, here what we can see is, you can see here the independent variable, okay, it is raised to the power -1. There is 1 by X, right? So the Y variable is linear, but the independent variable is not linear. Okay, in the denominator, what we have is, we have X to the power -1. Okay, then what we have is, we have polynomial functional form. So it can be cubic, it can be quadratic, it can be any, X variable to raise any power, right? So this is what is polynomial. Then what we have is interaction functional form. Here, what we have is, we have the product of, the variables. Okay, if we have beta1 x1, beta2 x2, what we're doing is, we are bringing in another variable over there, which is nothing but the product of the existing independent variables. So all these are important, but to understanding for your course, we need to deal only with double log model, then LIN-LOG, log-LIN model, apart from linear model, which are more than sufficient for you. Reciprocal polynomial interaction forms are not needed for you, okay, because you are not using it much in your thesis work, okay. And in reciprocal model, we have to take note of one thing. If beta 2 multiplied by 1 by xi, right? If this is the case, then what we have is we have a limiting and asymptotic value of beta 1. That is, if you are increasing x indefinitely, then the term beta 2 approaches 0, right? And y approaches the limiting or asymptotic value beta 1. Okay, so therefore, what you have is reciprocal models, they have built in them an asymptote or limit value in such a way that the dependent variable will take when the value of x increases indefinitely. If the value of x is increasing indefinitely, then the dependent value will take the limit value. Then it will approach towards the asymptote. So this is what reciprocal model is. Okay. Then interpretation, how we'll interpret, we'll see again. So this is level regression. It means linear regression. As you can see here, y is equal to beta naught plus beta 1x plus the ui error term. Okay, so here there is no log on y as well as no log on x. Okay, here the dependent variable is simply y. We are not transforming it. Similarly, we are not transforming the independent variable. Okay, then how to interpret? What is the interpretation over here? Given a change in x, what is the change in y? If we are changing x by so and so, what is the change in y? So this is what interpretation is. So delta y is equal to beta 1 delta x. Okay, so here if you are changing x by 1 unit, then we can see the change in y by beta 1 units. So if beta 1 is 0.4, then if x is changed by 1 unit, then y increases by 0.4 units. So this is what is your linear regression, right? Now coming to log level. So log, you're taking log of y, and then level means you're keeping x as such, right? So you see the dependent variable is log y, independent variable is simply x. Okay, here what we have, you see, percentage times delta y is equal to 100 into beta 1 delta x. So it means what? If we are changing x by 1 unit, we expect the y variable to change by 100 times beta 1. Okay, you have to interpret, if x is changed by 1 unit, then y changes by 100 into beta 1 value. If beta 1 is 0.4, then 100 into 0.4. So that is what the interpretation case of log level. Then what we have is LIN-LOG or level log, where the dependent variable is simply y, we are taking only log of x. So here, if we are increasing x by 1%, so wherever the log is there, we have to go for percentage, right? So if x is increased by 1%, then we can expect y to increase by beta 1 divided by 100 units of y. If x is increased by 1%, then y is increased by beta 1 divided by 100, or 0.01 times beta 1 of y. Then log modulus, you see the expression over here, percentage into delta y is equal to beta 1 into percentage delta x. Okay, so percentage change in y to percentage change in x. So if we increase x by 1%, we'll expect that y increases by beta 1%. If we increase x by 1 unit, we feel that y increases by beta 1 unit. Here, in terms of percentage, we are explaining. If we are increasing x by 1%, we expect that y increases by beta 1%. If beta 1 is 0.4, it means what? Y increases by beta 1, that is 0.4% for every 1% increase in x. Okay, so this is what interpretation is about all the models. So now we know what functional forms are popular and how to interpret it. For example, we know linear regression, that we already know, level. Now we know the interpretation part of log level. We know about level log, that is LIN-LOG, as well as log. So this is log-LIN, this is LIN-LOG, this is log. Okay, or log linear. Log linear is different, log-LIN is different, or we can say double log. Okay, now again let us see how to interpret beta 2. In the case of a model which is linear, where we have simply yi hat is equal to beta 1 plus beta 2 xi, then when x is increased by 1 unit, then y is increased by beta 2 hat units. So whatever be the value of the beta 2 hat slope coefficient, this is your intercept, this is your slope. If it is 0.4, if x is increasing by 1, then y increases by 0.4 units. Okay, if y is, for example, rupees per month, then if x is increasing by 1 unit, y increases by 0.4 rupees per month, right? Then in the case of the model over here, what we have is LIN-LOG model, because we're taking log on x side. Then y hat is equal to beta 1 hat plus beta 2 hat log xi. It means what? If x is increased by 1%, right, then y increases by 0.01 times beta 2 units, right? Then here, in the case of reciprocal model, we don't have direct interpretation, right? Fortunately. Then in the case of here, we have log-LIN model, that is log yi hat is equal to beta 1 hat plus beta 2 hat xi. If x is increased by 1 unit, then y increases by 100 into beta 2 percentage. If beta 2 is 0.4, then if x is increasing by 1 unit, then y increases by 100 into 0.4. Okay, 40%. So this is instantaneous growth. But what we're interested in is, usually now in your thesis, what you do is compound growth rate, CGR. So you can use the same model. You can use log-LIN model, and you can work out compound growth rate. How? For that, we have to go for anti-log. So of the slope coefficient beta 2 hat, we have to take anti-log of it. Then taking anti-log, first step. Second step is -1. So whatever value of anti-log of beta 2 hat you're getting, then -1. That difference, whatever you're getting, into 100. So that will give you your compound growth rate. It is over the time period, right? Then this is double log model, where we have log yi hat is equal to beta 1 hat plus beta 2 hat log xi. So if x is increasing by 1%, then y increases by beta 2 hat percentage. If beta 2 is 0.4, if x increases by 1%, then y increases by 0.4%. That is what is in case of double log model. Okay. Now here what we have is, apart from the slope, we can also find elasticity. Both are different. We know slope is different. That is, what is the change in y to the change in x? In terms of elasticity, what we are saying is, what is the percentage change in x to the percentage change in, what is the percentage change in y to the percentage change in x? So do you see dy by dx into xy by y? Okay. So this is what elasticity is. So now you see in case of linear, the slope is nothing but the simply slope, the coefficient is the slope, right? Okay. Now, in the case of your elasticity, you can find by the slope into x upon y. So if you want to find the elasticity of the entire function, you can take mean of x and then you can take mean of y. So simply the expected value or mean of x and then mean of y into slope, value of slope will give elasticity. In case of log linear, you can find slope by beta 2, then y by x. Okay. In the case of elasticity, the beta 2 value itself is the elasticity value, right? So this is what the case of the constant elasticity model, log linear or double log model, right? Then log lin, okay, where we have log y is equal to beta 1 plus beta 2 x. If you want to find slope, what you do is the beta 2 value, what you're getting by running regression into y. Then if you want to find this one, the elasticity, then beta 2 into x. What this formula is. Then LIN-LOG model, what we are doing is, so the slope coefficient, whatever you're getting, into 1 by x will give you slope. Okay. Then the slope coefficient into 1 by y will give you elasticity. Okay. So all these models are important. We should know what is linear model, how to obtain slope as well as elasticity. Slope you can easily obtain by running regression. In Excel, the way now how to run regression, if you do that, you can easily obtain slope coefficient. But from this slope coefficient, if you want to estimate elasticity, then you have to use this formula. So the slope coefficient beta 2, okay, into mean of x divided by mean of y. You have x values, you have y values. You take the mean of x values. Similarly, you take the mean of y values. So when you have the mean value or average of x and average of y, then when you are applying this formula, you can easily obtain the elasticity, right? Something like that you do for all. In the case of LIN-LOG, for the slope, after getting beta 2, then beta 2 into 1 upon x, you'll be getting here. Manually, you can calculate slope, right? And then in case of, if you're not doing it manually, if you're doing it, using Excel function, you can easily obtain slope. But if you're applying the formula of beta 2, okay, like if you have read in your course, you can also obtain beta 1, beta 2 manually, right? So when you are obtaining manually beta 2 value, and then when you are doing it, to obtain slope value, then you have to use beta 2 1 by x. But simply when you are running the regression function, you can easily obtain the slope value of the LIN-LOG model, okay, right? Now, choice of functional form. Which functional form to choose? Now we know we have linear model, we have double log, we have LIN-LOG, we have log-LIN. Which one to choose? It depends upon your theory. As I told you, theory is important. Econometrics is nothing but application of economics in statistics and mathematics. So theory is, you should have an economic theory. Before using any model, before collecting any data, before going for any analysis, you should have some theory. So the underlying theory is very important. Once you have theory, then it tells you which model to go for, okay? So apart from that, you can also go for, you should have some expectations, some assumptions. Whatever coefficients you're getting, the value of the coefficient or the direction of the coefficient or the significance of the coefficients. For example, for x1 variable, x2 variable, you're getting the coefficients, slope coefficients, right? So in your model, you have age, education and all, right? So you want education to be significant, but sometimes because of the model that you have used, education may not be significant. So it may not work in your favor. It means what? Even though, in your pilot survey or in your field, the data collection you obtain, assumed that education will come significant, but because of the wrong choice of the model, the variable is not coming significant. So you have to change the model and see. Okay, and so using linear model, you can go for double log model or log linear, linear log, whatever model is there, you can go for it, right? So that can tell you which model to choose. Then apart from that, now you can also choose model on the basis of the adjusted R-squared value or R-squared value. You can compare the R-squared value of, if you have got 4 different models. Okay, if you want to select one model, you can select on the basis of adjusted R-squared value. The model which gives you higher value of adjusted R-squared, or if you're not able to obtain adjusted R-squared, you can go for R-squared. The model which gives you higher value of R-squared, you can select that model. But the only thing is that the dependent variable should be same, right? So this is what is the choice of the functional form. The theory will tell you which functional form to choose, or on the basis of the interpretation of what you're going to interpret, or on the basis of your requirements of the independent variable and its significance or interpretation. And then if you are so much confused, you can leave it to the statistical property of the model. You have R-squared value as well as you can obtain adjusted R-squared value by the formula which we already discussed. And on the basis of higher values of R-squared or adjusted R-squared, you can select the model. Okay, so this is what the functional form is. Now, slope, we know what is slope. Now, change in y to change, additional change in y to additional change in x, that is slope. Now, what is elasticity? That is nothing but percentage change in y to percentage change in x. So the percentage change in y is given by, you can see here, delta y upon y into 100. Similarly, the percentage change in x is given by, so delta x into x by 100. So when you're putting that in the form of an equation, what you're getting is, after further processing, you will be getting delta y upon delta x into x by y, and the formula which we saw in the previous slide. So this is what is your elasticity of production. Okay, now let us see. So this is your linear functional form. Okay, where the predicted y, okay, is nothing but beta naught plus beta 1x. Okay, we have actual y and predicted y. Okay, x may vary, but we have population y, and then since we are not able to observe what the values of population is, we are taking sample, right? And that is what we are considering SRF. and a sample regression function, but that SRF should be close to PRF. Okay, so what we can best obtain is we can obtain predicted Y, and we can see how much the predicted Y is close to actual value of Y, whether there are any deviations, okay, that we can find. Now you see we have the values of X, right? And then we can predict the value of Y using the formula. Formula is nothing but beta 0 plus beta 1 into X. So we can easily obtain X, okay? The slope, okay, if I am giving you the actual Y value as well as the actual X value, then by running regression itself, you can obtain slope. But here in this case, the problem is we have only the actual value of X, but the predicted value of Y. Okay, the slope can be obtained by a simple formula, as you can see. Additional change in Y, you see here A, B, and C, right? So the B column pertains to predicted Y, you know, and then the A column pertains to the actual values of X. Okay, the value which you obtained using survey, for example. So the slope you can obtain by additional change in X to additional change in Y divided by additional change in X. Okay, so you see B11 minus B10 divided by A11 minus A10. So here we have B11 and then we have B10, right? So 25 minus 20 divided by 3 minus 2. This is what is slope. Okay, when you progress, when you have a series of value, you can find slope for every point, whatever you have. Okay, so there you can find additional change in Y to additional change in X. Then what you have is elasticity. How you can find, as I told you, elasticity is nothing but percentage change, right? So what is the percentage change in Y to percentage change in X? So you see the formula now. B10 minus B9 divided by B9, right? So here, what is B10 here? So 20 minus 15 divided by 15. Okay, then in the denominator what we have is A10, right? So 2 minus 1 divided by 1. So this will give you elasticity discrete. Then what we have is, apart from that, we have elasticity infinitesimal. Infinitesimal is what we can say point elasticity. Okay, you might have read now about in microeconomics point elasticity and arc elasticity. So this elasticity infinitesimal is nothing but point elasticity. Okay, elasticity at the particular point. So how to obtain this? The formula is very simple. As you can see here, what we have given. So there's nothing but slope. Okay, what are the value of slope? Slope into if you want to find point elasticity where the value of X is 1 and the value of predicted Y is 15, then you can obtain the point elasticity of this line, of this row, we can say, by beta 1, the slope which you are obtaining, right, into X divided by Y. X, value of X, then divided by value of Y. So like that, you can find elasticity infinitesimal for all the points. Okay, so for example, over here, what you can do is you can use same beta 1 into X, that is 19, divided by Y, that is 105. You can get 0.905. And then once you're obtaining, then you can also show the line of predicted Y. Okay, you can show this one, SRL, sample regression line, okay, using the predicted Y. So now you are able to understand, right? So here the predicted Y we are obtaining by a formula. The predicted Y is nothing but beta 0 plus beta 1x. We have the value of X, okay, and then we know what the value of beta 0 is. We know what the value of beta 1 is. Then you're multiplying it. So when we are introducing the values in this equation, we'll be getting predicted Y. Apart from that, we should also estimate slope, elasticity discrete, elasticity infinitesimal. This elasticity infinitesimal is nothing but your point elasticity. Okay, so we know what slope is, additional change in Y, additional change in X. We know what elasticity is. It is nothing but percentage change in Y, percentage change in X. So we are clear about all the concepts. Now, what is this one? Point elasticity is nothing but elasticity infinitesimal, what we have doing here is we are using the slope value over here. So slope, the whatever value you're getting, then multiplied by x by y. Okay, as you can see the the formula which is given over here. So you have to estimate for all the points in x for all the observations you can find. Okay, and then you can easily draw this SRL, sample regression line, by plotting x and the predicted y value. Okay, you'll be getting it. Okay, but if I'm giving you x and y values, so we have actual values of y and actual values of x, then you can predict y value by regression. By running regression, what you can do is you can see here. Once this window opens now, then apart from clicking on the output range, you can also choose tick residuals. So when you tick this residuals, so what you'll be getting is, then when you have the output table, you'll be having regression statistics, you'll be having ANOVA, and then you'll be having this one, coefficients. Apart from that, you'll also be having residual output, where you have predicted value of y. Okay, which is nothing but, as you can see here, this is your beta 0, beta naught, and this is beta 1. So in the case of the formula that we have used, predicted y is equal to beta 0 plus beta 1x. So here again, so beta naught plus beta 1x. What is the value of x? It can be anything, right? Like it is given over here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so you can see this is predicted price. This is residuals. Okay, or otherwise you can also obtain, if you're obtaining residuals, so the actual value of y minus residuals will give you predicted y value. Okay, that is the formula we know very well, right? Ui hat is nothing but yi minus yi hat. That formula you can use. Or yi is equal to yi hat plus ui. Okay, so you can use all those things. Now coming to double log function. So you see what is in double log? This is x, and then we have log x, and then we have predicted log y, and then we have predicted y, then we have slope, then we have elasticity discrete, then we have elasticity infinitesimal. Okay, so we are taking log on x as well as y. So here we can obtain the predicted value of y, log y. Predicted log y is nothing but, you see, beta naught plus beta 1 log x. We are not going for x, we are taking log x. So we have to incorporate the value of log x in this equation. Okay, and then everything else remains the same, because we know the slope is nothing but the additional change in output divided by additional change in input. That is additional change in y by additional change in x. Again, we have elasticity discrete, which is nothing but percentage change in y, percentage change in x. So this is your y and this is your x. Okay, you can find the percentage change, but here you have to get one thing. The important thing over here is, apart from getting predicted log y, you have to go for predicted y. Okay, here what is important is you have to find predicted y. Okay, if this is a predicted log y, right, then you take antilog of this. So anti-log of predicted log y will give you predicted y. Okay, once you have the values of all predicted y, this one you have to use to obtain slope, as well as this one, discrete elasticity, as well as infinitesimal elasticity. For all those things you have to go for using only predicted y and not predicted log y. Okay, so this you have to keep in mind, because you see the formula itself is very clear. Slope we are getting by d11 minus d10, that is additional change in this one. You see d is predicted y, right? So additional change in predicted y divided by additional change in x, the actual x value, right? Similarly, for elasticity discrete, we are going for percentage change in predicted y to percentage change in x. Now, how to obtain this point elasticity, that is elasticity infinitesimal, by using this formula. What do we have the formula? EXP, that is antilog, right? Exponential. So EXP beta naught. So what are the parameter value, right? We are taking EXP, exponential of it, antilog of it. into beta 1, the actual value of the slope, into x, that is actual value of the x, whatever you have, then to the power beta 1 actual value of the slope minus 1 into what we have is value of x, a10. A10 is what? Value of x, then d10, value of the predicted y. Okay, so this is giving you point elasticity. Okay, but if you want to obtain direct elasticity, okay, without worrying about the point elasticity, is nothing but simply the value of the slope itself is the value of the elasticity in the case of double log model. Okay, that is what we are getting. You see here, beta 1 is minus 1. This is the value of the slope coefficient, and what we are getting is the elasticity is nothing but minus 1 throughout, because that is what we are saying, right? It is a constant elasticity model. Log-log or double log or log linear model is nothing but a constant elasticity model where the value of the slope coefficient itself gives the value of the elasticity of y with respect to x. So you see, the elasticity is constant throughout, right? In the case of this one, your linear functional form, you can see the elasticity varies, right? Not constant. Okay, right. And then this one, semi-log functional form. In semi-log, it means what? We are taking log only on one side, not on both, either on dependent side or on independent side. First is log-LIN. It means what? Log of the dependent variable. You can see here, log of dependent variable, and x is used as such. You see, that is, we are not taking log on x. So x simply. Then again here now, apart from predicting log y, we should also go for predicting y, not just log y. Okay, so here the log y can be predicted by using this equation, nothing but beta naught plus beta 1x. Okay, so by incorporating the values in the formula, we'll be predicted log y, and then you see predicted y. We can predict y by antilog of log y. So when we take antilog of log y, we can get predicted y. And then what we have here, slope. We know how to obtain slope, right? Additional change in y, additional change in predicted y, to additional change in x. And elasticity discrete, we know how to obtain this, right? Percentage change in predicted y to percentage change in x, right? And then here again, what we have is we have percentage change of what? This percentage change refers to percentage change in predicted y. As you can see here, C9 minus C8 by C8, right? So this is C9. So 8.17 minus 7.39 divided by 7.39 will give you 10.5%. This is also constant throughout, right? And then what we have is we have elasticity infinitesimal, where the formula is given over here, where we can see antilog of beta naught, antilog of the intercept into beta 1, that is slope coefficient, into antilog of beta 1x into what we have is we have a10 by c10. A10 is what? This one, right? Value of x and then value of predicted y. So this will give you elasticity infinitesimal, that is every point will be getting, right? But if you look at the formula, in general formula we use, that is given over here. In the case of a log-LIN model, what we can do is we can obtain elasticity by simply multiplying the slope into mean of x. Okay, overall what we can do is we have x values, take the mean of x and then multiply with the slope, we'll be getting the elasticity. Okay, in the case of a log-LIN. Okay, that is why you can see here we are multiplying with x. You can see this formula over here. No, we are multiplying the slope value into x. Okay, to get the elasticity of the entire model. But if you want to find elasticity, point by point, observation by observation, then we have to go for elasticity infinitesimal, where you have to use this formula. Okay, the formula you can easily do it in Excel once you know what the formula is, right? Then coming to LIN-LOG model. Okay, LIN-LOG. Log-LIN is different. We know log-LIN is very important in the case of this is also called growth model, right? We can use this to estimate growth rate of anything. We can go for instantaneous growth rate as well as we can go for the compound growth rate. That you know already, right? Then coming to LIN-LOG model. In LIN-LOG model, what we have, you see, again, here what we are doing is LIN-LOG. It means what? We are taking log of x and then we are taking, we are keeping y as such, right? So here the y is predicted using the formula beta 0 plus beta 1 log x. So we know what beta 0 or beta naught is. We know what beta 1 is. The value will be given to you. If the value is given, then you can find predicted y. If the value is not given, then it means what? You have to first estimate beta naught and beta 1. Instead of simply predicted y, I may give you x values and y values. Using x values and y values, then running regression, you can obtain this one, beta 0 and beta 1 estimates. So once you have beta 0 and beta 1 estimates, then you can use this functional specification wherein you can find predicted y, right? Why then slope? We know now what slope is, right? Additional change in predicted y to additional change in x. Yeah? Then we have elasticity discrete, which is the percentage change in predicted y to percentage change in x. Yeah? So this is what is your easy here. Then what we have is, this is percentage change in x. Okay. Then we have change in y. We can also find what change in y is, right? Change in predicted y. You know, what is the additional change in y? That is minus 1.219 divided by minus 2.605 divided by minus 1.2. This is then what we have is, we have elasticity infinitesimal. Okay. So where we are doing, you see, beta 1 multiplied by the infinitesimal percentage change in x. Okay. So when you are multiplying the beta 1 by the percentage change in x, we'll be getting this one, elasticity infinitesimal, or you can go for this formula. In the formula, what we have is, we have beta 1, the slope, divided by A10. What is A? This one, right? Then into A10 by C10. So A is your x and C is your predicted y. So in that way, you'll be able to estimate the point elasticity or elasticity infinitesimal. Okay. So now we are very sure about the different regressional forms. Okay, functional forms of regression. Okay, and also we know how to interpret it. Also, we know how to obtain the slope values, how to obtain elasticity, and how to interpret. Interpretation is very important. Okay, whether I'll be giving you actual value of y, actual value of x. Okay, once you obtain it, then you have to interpret the slope. And then if I give you the question of asking you to find elasticity, then you need to interpret the slope as well as the elasticity. Okay, and then the most important thing is the log-LIN model, which you can use as growth rate. Okay, if you want to find growth rate of any economic indicator, you can use the log-LIN model. Then you can expect one question on the growth rate as well. Okay, I'll be giving you y and x, and then I'll be using you to find a growth rate, which is both instantaneous as well as compound growth. You have to find out. Okay, so all these things are important. Okay, please go through the video as well as this PowerPoint is shared with you. You can also go through it. Okay, the formulas are given in the PowerPoint itself. You take any data set, or I'll be sharing this data set as well with you. You can also practice it. In that way, you'll be, getting more confidence in handling data. Always remember, you should have an economic theory. That economic theory should tell you what model to choose. And if you're so much confused, you always have the R-square as well as adjusted R-square, which can tell you which one to use. Okay. Okay. Thank you. We'll meet you soon.